On our last video, we talked about the fact that scientists can use the refraction and reflection patterns of seismic waves to determine the structure and composition of the layers of the Earth by seeing how the waves act as they hit the layers and reflect and refract as they hit the layers. Because of changing densities between the layers, the waves will turn as they hit the layers because of the refraction, and by studying this, the scientists can figure out what the layers are like. And I gave an example of Andrija Mohorovic, which studied the Maho discontinuity as the layer that separates the crust from the mantle because of the sharp change in direction and speed of the wave as the wave hits that new layer. Now, basically, when you look at this at the global picture, what the overall pattern is that seismic waves, both P and S waves, tend to bend outwards as they go deeper and deeper into the Earth because the layers are getting denser and denser. And so they will bend as they move, as you see in the picture here, they will bend in this direction because as you go into the Earth, the layers are getting deeper and deeper. Also, remember that S waves will not travel to liquids, right? So that means that once the S waves actually hit the outer core, since the outer core is liquid, the S waves will have trouble continuing to propagate through this outer core that is liquid, and they will stop. And that means that one side of the Earth, this side over here, will only experience the P waves that actually go through the core. And notice how when we talk about refraction, that they will change speed but not direction if they're going dead on straight ahead into the thing. And the greater the angle of incidence, the greater the angle of change you're going to have. So that's why waves which are going at an angle will change the most. Either way, they will change more and more as they go deeper and deeper into the Earth because it's getting denser and denser. And that means the timing and the strength of seismic waves can help us give us a picture of what the inner layers of the Earth are like. And so one of the applications to use the seismic waves is actually learn about those layers. The lithosphere, the asthenosphere, the mesosphere, the outer core and the inner core, the structural layers of the Earth, will all discovered by refraction patterns of the seismic waves, and as well as how thick they are by the reflection patterns of the seismic waves. And we also study the compositional layers by understanding what the seismic waves are doing and how fast they're changing, and therefore determining the density of those layers and therefore what kind of materials they're probably made of, which was then subsequently confirmed by studies of volcanic activity bringing rocks from the bottom, and we can study the composition and confirm that in fact they were where we expected they were going to be. Now when you actually study the P and the S waves, you see an interesting pattern. Since P and S waves both bend outwards as they go deeper into the Earth, there's a pattern of dispersal from the epicenter towards the corners of the Earth, and you see that's happening there. And the waves which have a low incidence angle actually do hit the core, but only the P waves will actually get through. In this drawing, the P waves are shown in yellow. So you can see that the P waves will actually get through the core, but they will bend differently because they're now going through a liquid. And then they bend differently again as they go through a solid. And then the reverse happens as they go outwards towards the opposite side. The overall pattern results in the following. S waves marked in blue will never go to the outer core and will bend outwards, creating the fact that only this particular region here will actually experience S waves. So away from the epicenter, 105 degrees in each way, these are the only area that would experience S waves. People on the other side of the world will not experience S waves unless there's some sort of reflection. In other words, maybe a wave that hit over here, reflected to hit this side over there, but the actual original wave will not be heard, only the echoes will be heard. And we call that large area in the back that does not receive any S waves the S shadow zone. Okay? Now, the P waves will also refract outwards, and as they hit the core, they will also refract in a particular pattern, which leaves these two areas here, these two chunks, that will not experience P waves, and we call those the P shadow zones, which extend from between 105 and 140 degrees on either side of the Earth. And this is happening because of the structure of the Earth, and you can use that to determine the actual shape of the Earth. You can also use seismic waves to determine where the boundaries are at. If you actually trace the location of all the divergent boundaries, and you will see that there's a lot of earthquakes happening along those boundaries. See, I'm actually tracing the divergent boundaries around the world, and you can see how there are so many. And look how a new divergent boundary is actually forming right there. And you can actually trace that, and you see that Those are the divergent boundaries of the world. Then you also have the convergent boundaries, and yes, those will also have large earthquakes. And you see that when you trace them, you actually find a picture of tectonic plates as well. So you actually can draw the tectonic plates of the world by putting the boundaries in the map, right? So you can see how they actually work out. And you also have transform boundaries, which also have a lot of earthquakes. So you can actually draw them to locate all the transform boundaries. And so you get a picture that looks just like the tectonic plate picture by actually tracing down the earthquakes. And notice that there are some earthquakes that will happen away from boundaries, and those are the hot spots, right? Or the location of ancient boundaries. So you can also use earthquakes to find things like volcanoes. Volcanic activity, or that magma that's moving on the ground, will move around the rocks, will cause deformations of the crust, which will cause folding and bending of the rocks, which will cause the rocks to rupture and form elastic rebound. And so volcanic activity will also cause earthquakes, so you can use earthquakes sometimes as evidence of volcanic activity. You can use earthquakes to find the presence of boundaries. For example, there's evidence that there's subduction happening at convergent boundaries because of earthquakes. Look how many earthquakes happen along the collision between the Nazca plate and the South American plate, and you can actually see the number of earthquakes happening indicates that there's a plate subducting under the other. And you have to actually use the seismic waves to do a topography study, like we talked about before. If you can see the layers and how they're shaped and stuff, you can actually get a picture that a lot of the earthquakes will happen along that subducting plate. So you can actually see the pattern. Look at how the earthquake actually traces a block that seems to be going underneath another block, and that is actually that subducting plate that you're seeing changing and bending because of the subduction that's happening with it. So earthquakes can actually be used as an evidence of a subduction that's actually taking place, because we don't see the subduction happening, we only see the trench. And so how can you tell there's actually a plate underneath there? You can tell because you can see that the earthquakes are deep underground and actually form the shape of the subduction zone that you're expecting happen. And when you do a topographical study, you see that at the trench, if you keep following down the trench, you will see a pattern of earthquake activity mirroring what's expected from a subducting oceanic plate underneath a continental plate. So seismic activity can also be used to help you identify subducting plates. All right? And so you can use earthquakes to determine plate boundaries, hotspots, and rifts. You can use it for evidence of volcanism, and you can also use as evidence for subduction. And in addition to also using it to determine the layers of the earth that we talked about. All right? On the next video, we're going to be talking about how to measure these earthquakes in order to do all these things. See you guys then.